Hi, I'm Courtney Carr, Director of Marketing and Education for IAPD. Thank you for joining today's e-training webinar, Introduction to the IAPD Thermoplastics Rectangle, presented by Chad Presida of Harker & Associates. During the presentation, you may submit questions into the Questions tab on your webinar toolbar, and we will answer them at the conclusion of the presentation. Following the webinar, you will receive a link to a survey. Once you have completed the survey, there will be a link to download the presentation slides. A recording of today's webinar will also be made available for download on the IAPD website. Chad Presida is a sales representative at Harker & Associates, a member of the IAPD Environmental Committee, and an IAPD trainer for the Introduction to Plastics live training workshop. I would now like to turn the presentation over to Chad.
Good morning, everyone. Thank you, Courtney, for the introduction. I appreciate it. And I want to thank IAPD for allowing me to present this webinar today. So today we're going to review the IAPD Thermoplastics Rectangle. So many of you may already be familiar with the rectangle or perhaps another chart. And for some of you, this is going to be a brand new concept. Either way, this webinar is going to be designed to cater to all skill levels. The thermoplastics rectangle is an incredibly valuable tool in our day-to-day lives in the performance plastics industry. The performance thermoplastics rectangle can help us with material selection and helping to cater to our customers' needs. So whether you're a buyer, you're an engineer, you're a sales rep, no matter your role or who you're working with, this is going to be an incredibly valuable tool. So today we're going to review the differences between amorphous and semicrystalline polymers. We're going to look at how the rectangle is laid out and designed. We're going to look a little more in depth at the rectangle and its contents. And then finally, I'm going to try and bring it back home to everyone and give an example of how we can use the rectangle in our day-to-day lives as performance plastics experts. So let's begin. Okay, so here we have kind of a busy slide, and I don't want your eyes to glaze over. The contents can be a little overwhelming, and for those of us who don't have a chemistry degree, myself included, this can be a little overwhelming, but I promise this is all gonna help with a foundation for us to understand the rectangle on the next slide. So in the performance plastics industry, we have two kinds of thermoplastics. We have the amorphous and the semicrystalline. The amorphous thermoplastics, the polymer chains are in a random arrangement. The molecular structure is incapable of forming regular order or crystallizing, with molecules or portions of molecules regularly stacked in crystal-like fashion. The molecular arrangement is randomly twisted, kinked, and coiled. The alternative is the semicrystallines. The semicrystallines, the polymer chains, they form a regular pattern. The molecular structure forms regular order or crystals, with molecules or portions of molecules regularly stacked in crystal-like fashion. The molecular arrangement is arranged in an ordered fashion. So it may help to think of this is a pretty basic analogy, but it did help me. Think of it like spaghetti, okay? So your amorphous plastics is your cooked spaghetti, right? So there's a random arrangement, they're incapable of forming a regular order or crystallizing. Your semicrystallines, those are cooked spaghetti, right? So they are, they're stacked in a regular pattern. So I know that's a little simple, but it does sort of help us to understand the differences between amorphous and semicrystalline thermoplastics. So now we're going to have our first look at the rectangle here. So this slide helps us see how the thermoplastics rectangle is designed and laid out. So you can see that we have our amorphous plastics on the left, the semicrystalline plastics on the right, and then a third type of thermoplastic, which we haven't addressed until now, which is our imidized plastics. So I'll take a moment here just to address imidized plastics. Imidized materials are polymers that have been modified on the molecular level to improve certain key characteristics. So whether that's to improve the thermal range, stiffness, strength, these are very very specific plastics for specific applications and very, very high grade plastics. We're not going to spend a whole lot of time on them, but it is important, which is why they're included in the rectangle. So I wanted to just discuss real briefly what those are, and we'll come back to those on the next slide. So let's start in the bottom left-hand side. So you can see that we have the amorphous plastics, but then we've further broken that down into the high performance, engineering, and commodity. And then you can see on this, on the flip side, the semicrystalline is broken down into the same categories. At the very bottom, we have the key characteristics of each amorphous and semicrystalline thermoplastics. So let's go to the next slide and let's take a closer look at the rectangle. So first, I'd like to discuss the margins. So you can see that on the left-hand side and the right-hand side, we have arrows. Those arrows are going up, and you can see that as we go from commodity to engineering to performance thermoplastics, we're going to see an increase in things like thermal resistance, performance, chemical resistance, and other physical properties. Now, this is a general rule of thumb. However, it does typically hold true as you go up and go from commodity to engineering to high performance thermoplastics. So let's begin with the key characteristics. So before I get too far into the key characteristics, I do just want to mention that these are general rules. There are plastics out there. You may see some amorphous plastics that don't exhibit this key characteristic, perhaps because it's been modified or there have been additives included in the polymer. That's a webinar in and of itself. We're not going to get too deep into that. So just keep in mind that as we're going through these key characteristics, these are basically just rules of thumb and general key characteristics. So let's start with the amorphous on the bottom left-hand side. Amorphous plastics tend to soften over a broad range of temperature that can make them easy to thermoform. They tend to be translucent or transparent. That's typical, but not always the case. They do typically bond well using adhesives and solvents. They're prone to stress cracking. They're poor fatigue resistance, and oftentimes used in structural applications only. You're not going to see many of these in bearing and wear applications. So let's go up to the commodity, the amorphous commodity thermoplastics. So the key characteristics here are low cost, low temperature resistance, and low strength. Here you're going to see plastics like your acrylic or your PVCs. Going to the next level, you're going to see that the characteristics are going to improve in the engineering and the amorphous engineering thermoplastics to moderate temperature resistance, moderate strength, good to excellent impact resistance, and good dimensional stability. But with those increased key characteristics or improved key characteristics, you are going to see an increase in cost in many of these materials. In this product family, you're going to find products like the polycarbonate. So the next is the amorphous high performance thermoplastics. So this is the highest level of amorphous thermoplastics. You're going to see the highest temperature resistance, the highest strength and stiffness, and you're going to see excellent water and steam resistance. But again, as you go up in levels, we're going to see that these are also the most expensive and highest cost of the amorphous materials. In here, you'll find plastics like polysulfone. So we're going to go back down to the semicrystalline, and we're going to go through those key characteristics quickly. We're going to start with the sharp melting point that can make them difficult to thermoform. They tend to be opaque. They're difficult to bond using solvents and adhesives. They have a good resistance to stress cracking, good fatigue resistance, and are typically good for bearing and wear in structural applications. So some of the semicrystalline commodity thermoplastics, the characteristics of the semicrystalline commodity thermoplastics is they're going to be lower in temperature resistance and strength. They are going to have a low coefficient of friction, making them good for that bearing and wear. There's going to be near zero moisture absorption, good electrical properties and toughness. However, they are going to be difficult to bond. Materials you'll find in here are the high density polyethylenes and low density polyethylenes. And these are going to be the lowest cost of all the semicrystalline thermoplastics. So going up to the semicrystalline engineering thermoplastics, we're going to see again that increased cost. But with that increased cost comes a moderate temperature resistance, moderate strength, good chemical resistance, good bearing and wear properties, low coefficient of friction, but again, still difficult to bond. This is where you're going to find products like your nylons and your acetyls. And finally, we have the semi-crystalline high-performance thermoplastics. So these are going to be, again, the most expensive of all the semi-crystalline thermoplastics. But with that increased cost, we get high temperature, high strength, good chemical resistance, good electrical properties, still that low coefficient of friction, and good toughness. This is where you're going to find products like your PVDFs and your PTFEs. Finally, last but not least, we have the imidized at the top. So the imidized thermoplastics and products are oftentimes used for very specific applications, as I mentioned earlier. Now, these products they have excellent physical properties, even at temperatures above 400 degrees Fahrenheit, excellent electrical properties, excellent dimensional stability, and low coefficient of friction. However, these are incredibly expensive. They have a very high cost per pound. Oftentimes, if our customers are looking for imidized materials, they may already know, or they may have a very specific application, and it's fairly easy to focus on or choose an imidized material for their application. This is where you're going to find your polyimides and your polyamide-imides. So let's bring this back down to our level and think about how we can use this for perhaps making a material recommendation to our customers. Let's say Mr. or Mrs. Customer calls us one day and says, hey, I have a stamp collection. I would like to put it in my office, but I don't want my grubby grandkids putting their fingers all over it. So I want to create a display case. Okay, I'm going to probably glue it together. I don't want to break the bank in doing that. Perfect. So I think with that, we have enough information to come to the rectangle and at least make a material selection to start. So let's start with the key characteristics, and let's start on the semi-crystalline side. So has a sharp melting point, no big deal. We're just building a display case for these stamps. Difficult to thermoform, again, not a big deal. Tend to be opaque, ooh, that could be difficult. He is going to want to show those stamps to all the people that come through his office. Let's not rule it out yet. Let's look at the next one. Difficult to bond using adhesives or solvents. Well, he did say he wanted to glue it together, so I think we could probably stop right there and just jump over to Amorphous and see if that has characteristics that would be more beneficial to us. So soften over a broad range of temperatures, sure. Easy to thermoform. He's probably not going to thermoform it, but good to know. Tend to be translucent or transparent. All right, I think we're on the right track here. Next, bond well using adhesives and solvents. Great. Prone to stress cracking, poor fatigue resistance. Neither of those are that big for us. Structural applications only, not bearing and wear. Well, this isn't going to be a bearing or wear application. So let's go up a level and let's go to the amorphous commodity thermoplastics. Let's look at those key characteristics. Low cost, great. Customer said he didn't want to break the bank. Good start. Low temperature resistant. Well, it's going in his office, so I don't think we have to worry too much about that. Low strength resistance. Again, not a big deal, just a display case for his stamps. So I think we could say that that's probably a good starting point, but let's look at the engineering thermoplastics just in case. Moderate cost, getting a little expensive. Moderate temperature resistance, not a big deal. Good to excellent impact resistance. I don't really think it's going to get beat up too much. Good dimensional stability. I think that's probably overkill and we could go back down to commodity. So if it were me, I would choose one of the materials under the commodity, amorphous commodity thermoplastics. I would probably choose an acrylic for this application. So that's a way that we can bring it down to our level and understand how we can recommend and at least get an idea for proper materials to recommend to our customers as they come to us with their needs. Very rarely has a customer ever come to me and said, hey, I really need a piece of polysulfone. It does happen, and typically when they need it, they know they need it. But oftentimes in our jobs, we are making material recommendations based on the application, and the rectangle can help with that. So for those of you that have the Performance Plastics manual or guide from IAPD, and I recommend that you all do. It's a great guide. I have it on my book, or on my desk, excuse me. The flip page on the other side of the rectangle is this. And what this is this it shows the 17 top used thermoplastics in our industry, and it gives you a side-by-side comparison based on properties. So again, perhaps you focused in on a certain product, but you don't know how, or a material, but you don't know how it would compare to other materials in, say, coefficient of friction. Well, we have that here in a graph at IAPD. You can just compare it to different thermoplastics and understand perhaps what material would be best suited for your customer's application. So what have we covered today? So we discussed briefly amorphous versus semicrystalline and gave us a strong foundation on the difference in those two polymers. We also briefly discussed imidized plastics. We talked about how the rectangle is designed and how to help us navigate it. We further reviewed the contents. And finally, we discussed how we can use the rectangle and these graphs in our day-to-day lives to make material recommendations to our customers and make us more effective performance plastics professionals. So with that, I think I'll open it up for questions.
Thank you, Chad. As a reminder, please submit any questions using your webinar toolbar. As we wait while you type your questions, I'd like to remind you all that you can download the IAPD Thermoplastics Rectangle and the Plastics Property Comparison Graphs for free on the IAPD website. Once you're on the website, just go to the Training and Education tab. It's also available in your copy of the Introduction to Plastics textbook. We'll give it a minute or so while people type their questions. All right, I don't see any questions coming through, so this will conclude our presentation. As a reminder, you will receive a survey about today's presentation. Once you complete the survey, there will be a link to download the presentation slides. A recording of today's webinar will also be available on the IAPD website on the webinar page. Thank you all so much.